Hello and welcome. Today, we're diving deep into something that honestly makes our entire digital world tick. It's something you rely on every single second, but probably never even think about. Keeping time. Not on your wrist, but inside the vast, complex networks that connect everything. We're talking about perfect, synchronized time.
I mean, just think about it for a second. What if your phone and the cloud had a tiny disagreement about what time it is right now? Suddenly, your video call stutters, your online game glitches out, financial trades worth millions could go sideways. That shared sense of now isn't just nice to have, it's absolutely, fundamentally critical. And that's what synchronization is all about. At its core, it's the language of time for technology. It's what allows all of our electronic systems, from the tiniest chips on a circuit board to massive globe-spanning networks, to operate on one shared timeline. It's making sure everyone is marching to the exact same incredibly fast beat.
Now, to really get why this is such a hot topic today, we need to look at two very different worlds that are suddenly colliding: the world of telecom and the world of data centers. You see, for a long time, these two have had completely different relationships with time. So on one side, you've got telecom networks. Think about your cell phone. For things like handing your call from one tower to the next without dropping, they need insanely precise timing. It has to be almost perfect. Then, on the other side, you've got data centers, the engine room of the cloud. And historically, they've been way more, let's say, chill about how precise their clocks are. And here's the heart of the problem. Telecom networks demand accuracy down to the microsecond. That's a millionth of a second, or even the nanosecond. It's hard to even wrap your head around. Data centers, meanwhile, were totally fine operating in the millisecond range. That's 1,000 times less precise. For decades, that was fine. But things are changing, and they're changing fast. So why the big change? Well, we're in the middle of this massive industry shift. Welcome to the Great Convergence, where the world of super precise telecom is smashing right into the world of data centers, and it's all being driven by 5G. You see, new 5G setups, especially this idea called O-RAN, or Open Radio Access Network, are blowing up the old way of doing things. Instead of having one giant proprietary black box from a single company, O-RAN lets you break the network apart. You can run different pieces of the 5G network on standard off-the-shelf servers. The exact same kind of servers that fill up data centers. And this is a total game changer. By putting critical 5G hardware, like this distribution unit, or DU, right inside a data center, you bring all that 5G magic, the huge bandwidth, the near-instant response times, so much closer to the apps that desperately need it. We're talking autonomous driving, real-time AI, advanced robotics, you name it. So this brings us to the million-dollar question. You've just moved this high-strung, time-sensitive piece of telecom gear into a data center. How on earth do you give it the hyper-accurate, telecom-grade clock it needs to even function? The data center's built-in clock just won't cut it. You have to somehow pipe in a super precise time signal, say from a satellite or an atomic clock, and get it to the right place. But how? Okay, so how do engineers actually solve this puzzle? To get that perfect time signal from point A to point B, they have a whole toolbox full of what we call sync transfer mechanisms. Let's pop the hood and see what's inside. Generally speaking, all the solutions fall into two main families. First, you have physical layer transfer. Think of this like the timing signal. The actual frequency or beat is baked right into the electronic signal traveling down the wire. The hardware at the other end just listens for that beat. The other way is the protocol layer. This is more like sending little digital postcards. You send a data packet that says, hey, by the way, the time I sent this was exactly this. And the receiver uses those timestamps to set its own clock. But here's the thing. There's no one magic bullet that solves everything. Picking the right method is all about trade-offs. You're constantly balancing performance against cost and what kind of hardware you have. It's really about picking the right tool for the specific job you're trying to do. So let's look at the most common options, because they really tell the story. At the bottom of the ladder, you have NTP, the Network Time Protocol. It's all software. It's what your laptop uses to sync its clock.
And, well, it's only accurate to a few milliseconds. Not nearly good enough for 5G. So you step up to PTP, the Precision Time Protocol. Now we're talking. This gets you into that microsecond range 5G needs, but to do it right, you really need some dedicated hardware to handle the time stamping. And then for the absolute best performance, you combine PTP with a physical method like Sync-E. That gets you into sub-microsecond land, but it's non-negotiable. You need specialized hardware all the way. And for those applications that need the absolute bleeding edge of performance, I'm talking particle accelerators, high-frequency stock trading, engineers pull out the really advanced hardware-heavy stuff. You've got Sync-NZ, which we mentioned, and then protocols with cool names like White Rabbit that can get you to sub-nanosecond accuracy. That's just mind-blowing. Of course, the most direct way is just to put a GPS receiver on every single server, but as you can imagine, that gets crazy expensive really fast. So these tools are what we're using to solve this huge convergence problem today. But you know how technology is. It never, ever stands still. Researchers are already pushing the boundaries, working on the next generation of synchronization, and asking, how can we do this even better?
So what's coming? Well, we're seeing work on things like specialized protocols just for data centers and smarter distributed algorithms. But the really wild futuristic idea is the quantum clock. Seriously, imagine using the bizarre properties of qubits, the heart of quantum computers, to keep time with a level of precision that makes today's methods look like a sundial. That's where we're heading.
And that brings us to one last really fascinating question. This whole convergence of telecom and data centers is forcing us to become masters of time on a scale we've never seen before. So now that we're on the verge of being able to synchronize our entire digital world down to the nanosecond, to a billionth of a second, what's next? What incredible new technologies, what new applications we can't even dream of today will we build with that power?